how to handle secret network together with Solana as part of secret confidential computing layer. Secret has a connection mainly to EVM chains, but that's also something new that we wanted to showcase during this hackathon, and we hope someone will, pick it up and try to do a hackathon project with it, is actually a connection to Solana. So I won't get too much into the details on how we're going to do it. I would, however, give you like a rough overview on how it works. Won't be too much, since the ideas behind it are exactly the same as they are for EVM secret path infrastructure. So I will just give you like a quick link to the docs for this. Okay. Okay, let's go. Okay, so for this, I would just reference to the docs. And as you already know, we have our EVM toolkit, which is, has a lot of examples on how to use secret path in connection with EVM chains. So we have a lot of EVM chains supported. If you look at our current state of how much we support, we do support a bunch going on from Ethereum, Scroll, Polygon, Optimism, so a lot of L2s, as well as some major L1s. Now, the thing is, the whole structure of secret path itself is pretty much the same for EVM as well as for Solana. The only difference, obviously, is that the whole Solana secret path gateway, etc., is all written in Rust, which is the native language for Solana. So the whole, for the developer itself, a lot of things change, but for the user, usually, if done right, not a whole lot of things will actually change from the flow. Also, the logic between the EVM and the Solana secret path is actually compatible. So that means you as a developer could actually build a dApp that spans across EVM as well as Solana, which means basically the whole secret path connects Ethereum and Solana together using secret, doing it in a confidential manner. That means for you, you will have a lot of possibilities to just explore that kind of direction. We're not expecting to have like a lot of projects using this idea, but especially since we're leveraging confidential computing, I think there will be like some very nice use cases, smaller use cases, but super nice use cases that can be done with this, especially if you're spanning across two whole completely different ecosystems and chains such as EVM, EVM chains and Solana. So for our today's example, we're going to use something really, really easy, which is we are going to do like one of the simplest examples today. We want to keep it light for this workshop because it's one of the first ones that we're actually using this. And it is actually just generating random numbers using secret networks. So what we're doing is we are on Solana. And we are on Solana right now, and the user needs to request some random words, some random numbers. For our example, we also offer like a key value store, which is pretty much the same idea behind it. You can just store every value that you want. So you can use Solana, for example. A user could potentially use secret path and secret itself using Solana. And the idea behind it would be that the user, for example, needs to, pass or like just store an encrypted string, some encrypted information onto secret. And the thing is, and this is like one of the key advantages of just using secret directly. In that case, he would be able to do it directly from Solana, directly from his like home network without ever really having to leave Solana. So a developer could potentially just, construct a use case or like have a dApp that uses secret in the background, and the user wouldn't even feel that secret is used in the background really. And the user just experiences Solana as he does this, always does. So we have two examples here in our docs, and I would definitely recommend looking into the docs for the key value store tutorial. Since this is a bit more complicated, I will just go into the VRF tutorial here. And in that case, we're really just going to use we're just going to generate some random numbers. The core ideas behind both of these tutorials are the same though. So what really changes is just the use case, but not really the, I'd say, the core ideas of how to do the encryption and how to handle the secret path contracts doesn't really change. The only thing that really changes is just, one of the, which acts like an extra layer of complexity is just, storing and retrieving values. So for our VF demo, we're mainly going to go through one of the examples that our DevRel team has made. Specifically, Sean Rad, who did like this amazing tutorial, which I'm going to go through with us together today. So since we can jump straight into it, and what we can do is essentially the front end is really where the whole magic happens. So for secret path itself, I'd say the main footwork that a developer has to do is going to be in the front end, because a lot of the messaging and the messages that the user is going to do needs to be encrypted on the front end. Obviously, the idea behind secret path is that a user encrypts a message locally on his browser, and then sends an encrypted blob that he has into Solana, and from there on, it's going to be handled by secret path. So for the main work that a developer is going to do is mainly using the front end and encrypting the messages, then signing the messages, and then submitting them to the chain. That's the main work that a Solana developer has to do. So just to give an example of what we're actually accessing, I can just give an example. So what we're actually accessing is this contract here on Solana, or in that case, it's not really like a contract. Obviously, in the original sense, in Solana, these things are called programs and accounts. So we have a program that contains the executable code, and then this program usually has accounts that are derived from this program address. And the information for this, basically, on how to pick that up, that's all stored in here. So we have the program ID, and from the program ID, you can completely generate account addresses, etc. That's going to be part of this tutorial here. So just to give you like a rough workflow on what we're going to do, which is exactly the same for EVM as well as for Solana, that doesn't really change. That's one just kind of keep to the, you can actually use the documentation for this even, because it's, it's also mentioned in the hackathon docs, so you can directly go there, and you can directly see basically what the architecture is. Just to give you a rough idea of the architecture for this workshop, it's not gonna, I'm gonna keep it rather light, which is you as a front end, so the user on the front end encrypts a message, sends it into his personal contract, or you can directly send it to the gateway contract. It doesn't really matter. The important thing is a user creates his front end and creates an encrypted message. Exactly. And what the user then does is you send it to the master public gateway. This can be on EVM, this can be on Solana. Then this is going to get picked up by Secret Network's relay network. So this is just independently maintained by some groups here. And then this trustless relay network sends the encrypted messages that came from the original gateway on Solana or EVM into Secret, into a master private gateway, which is a smart contract on Secret Network, which is encrypted and private by default. So the whole idea behind this really is, behind Secret Path, is really that we have this secret gateway on a Secret Network side that encrypts and signs messages, and this is what allows you to essentially verify that the message was correctly executed inside of Secret. And then the contract itself here, the master gateway contract, can then verify and then attest, essentially using a signature, that this execution was done correctly. So it's just a simple signature check that checks the result. and that is passed back to the user essentially. So you do some execution in secret. The secret network gateway then calls like your contract, whatever the dev developer has made. That's up to you basically for the hackathon. And then the result is sent back, encrypted, unencrypted. Actually, you can actually opt to encrypt it. That's really up to you. But the gateway contract itself will just sign this packet and then send this packet back to the user where it can be decrypted, or it can be used in a different smart contract, whatever you really like. That's really up to the developer to decide. But the core idea behind it is this whole secret path gateway stuff, and the whole secret path, the whole idea behind it really lies in this contract, handling the messages and signing messages using the encryption features of secret. So since the contract is private by default, there is a private key inside of this contract, which is not available to anyone to see. Only the contract knows about this key, and this private key is then used to sign messages. So that way you can always attest where the message came from, and you can be sure that this gateway contract was actually signing that message. And using this idea, we can now, we had a lot of success using the secret path on the EVM. In the EVM space, we had several hackathon projects. Some projects are starting to build on it just for the mainnet production builds. And now our next really big thing is really to bring this into the Solana space, because obviously the overlap between Solana and CosmWasm is much bigger since both are using Rust. So let's jump into the tutorial that we have here. I can also show you how it's going to look like in the end. We have the VRF demo, and we have the Solana VRF demo. Oh. Let's pick it differently. Okay, this one here. So essentially, this tutorial is going to follow be the following. We are just going to generate a random number using encrypted payload. So we're just going to encrypt the payload, sign a payload, and then send it into Solana. And then from there on, the secret network, secret path will take over and will generate the random number as well as return it to the contract. So to give you an idea on how this looks in the flow, I will just give you a demo, and then we can basically pick up how to do it. Let me just switch screens for this. And pick a new screen and pick that one. Okay, let's pick that. Okay, so we are connected to Solana, to this account, just test account. And what we're gonna do is we are using Phantom Wallet actually. Yeah. So we're using Phantom Wallet, and we just connected to Phantom. And now what we're going to do is we just press the connect button. So what it did is actually, as you can see, it created a raw payload. Then it already encrypted that payload using the front end. And it generated a payload hash. That is the thing that we're going to sign on Solana. I can just give you like a screenshot of it because it's quite nice to see. I'm going to put it into the main stage chat. So this is basically what you can't see. And we're just going to sign that payload hash here. So this is just the base64 encoded payload hash that we generated out of this secret path payload here. We're going to sign this to attest that this was correct, and it spits out a payload signature. And now we are going to sign a message that will send this message into the network. Exactly. So let's do that. And as you can see, it just gives you like additional information, which is the public key used doing encryption. And we have announced that also used to encryption. And the thing is, now we actually got a TX hash, which is we send in a message into Solana. In this case, it's to Solana DevNet. and has completely the whole instruction data, which contains the payload and contains everything that we need. And as you can see, inside of the program log, it spits out a instruction to log a new task that is picked up by the secret path relayers. So what we did is we did we created a raw payload, we encrypted it using secret path, which is going to show you how to do it. We created a payload hash, signed this payload, and then we sent it into Solana. And from there on, we logged a new task, and now we can just check the callback here just by hand. In that case, it would probably be picked up by your program. And as you can see, this message was sent in 1 minute ago, and it was basically always returned almost immediately back, as you can see. So we got the message back, plus the instruction data, and the secret path relayers will take care of everything mentioned here. And as you can see, it returned us 18 times 32 bytes of random data, which is something that we can use in our case. So for example, it's invoked the callback test, and this then returns just the callback number. So in that case, what we had is we just have like a small example inside of the secret path contract, which you just can always call just to check if your callback has been successful or not. I'm going to show you how that's done. But essentially, we just created a bunch of random numbers for super cheap and super fast using secret path directly on Solana. Since you're already using Solana, I can assure you that Solana is much harder to handle than just this front end. So we're going to switch now to the code part of it and see how it's going to be done. Let's switch here to the front end encryption. Yeah, let's switch here. So we switched to the other encryption example. So essentially what we're going to do is the following. This is the whole code for the contract for the front end, and this is how we're going to handle the whole thing. You need to keep in mind that we're mainly doing 3 main things, which is first, we're going to create a payload, then we're going to encrypt it, and then we're going to sign it. This is like one of the 3 key things that secret path is really, that makes secret path much easier to use than most other techniques that we can have for requesting randomness or anything else. So what we're going to do is first, this is main information. As you can see here, the gateway public key, as well as the routing contract. This is everything that you will get from our documentation inside of Secret in our secret docs. So we have an encryption key that encrypts the messages using ECDH. So what you have is you essentially have a public key that comes from the gateway, and you as a user on the front end actually create your own private key pair and use ECDH to create a shared key between you and the gateway. And that way you can always sign encrypted messages that are only visible to you and the secret network gateway that is able to decrypt them. So what we first do is we load in this public key that we use for encryption. So what we have is we use CHA-20 poly 1305, just really the standard encryption techniques that we use here. There's no additional fancy stuff going on. We really just use well-tested encryption methods. Exactly. So let me just wait a sec. So first of all, when we go into this decryption stuff, is there like already some questions that we might want to answer at that point? Might be interesting for you to see. Maybe something that you didn't know at that point. Okay, since we don't have any questions, we can just go further, I guess. So our idea is mainly to see, okay, well, how do we first encrypt the whole public key? And how do we do the encryption? And the next thing is, what are we actually going to call on secret network? So what we're doing is, here we're defining the encryption key, the public key just for doing the encryption. And then next, we're going to define what contract we're going to call. In this case, this is just a randomness contract that provides randomness. So as soon as you call it using secret path, it will just give you back as much randomness, as much random numbers as you want. And this is the code hash of the code to ensure that we're actually calling this version of the right contract. Next, we're going to do just simple, normal, connection to Solana. So in that case, we're just connecting to the DevNet from Solana, and we're going to get our provider. Obviously, in our case, it was just Phantom wallet. Could just be any wallet which you want. Could be any wallet compatible with Solana. So we're going to get our provider, and then we're creating our wallets, and then we're creating our anchor provider. So in that case, it's just mainly just setting up the provider. That's it. Feel free to just copy paste that stuff because it's quite easy. Next, we're going to just import our program using the IDL. So in that case, secret path for Solana was completely written in the anchor framework, which our goal was to really have a simple to use framework, which Anchor is amazing for. So we're just using Anchor, and the IDL is also, of course, visible in the repo as well as in the docs. So you can always just go to the docs and also look at the IDL there. But it's also, of course, included inside of the project. If you look at it, it's part of, we included that as part of the Solana Gateway JSON file, as you can see. So we are importing our program, and then just the normal setup would just be pretty much normal to what you would use for setting up any interaction with a Solana program. Now, this is where the interesting part starts. This is really specific to secret path, and this is really the part where you would really need to be careful in what you're doing. So the idea behind secret path, as I told you, is essentially we are going to encrypt a message using Charter 20 Poly 1305. So we're just going to encrypt a payload message. And the way to do it is we take the gateway's public key, and you as a user here locally create your own private key. So what you do as a user is you create your own private public key pair, as you can see here. So we're just creating some randomness on your local device. Then we're going to take these bytes, and we're going to create a new, based on that private key, we're going to create a new public key. So which means we have a private public key pair, and at that point, we are going to actually do ECDH, so which is elliptic curve Diffie-Hellman. For those of you who want to know the details, what ECDH does is it will create a shared key between the private key of the user and the gateway public key. And just for you as an idea, we're doing this on the user's front end, and what the gateway contract on Secret will do is it will do exactly the opposite. It has a public key from the user and a private key from the gateway. So this is basically what the gateway will do. It will create also a shared key between the public key that we got from the user and the gateway's private key. So that way we can securely exchange information between the gateway and the user public key without revealing any symmetric key that we need to. So that's quite convenient. So obviously the idea behind this is to share or establish a secure connection between the gateway and between the users and device. So by this, we are generating a shared key. This shared key is then used to really do the encryption of that payload that we have, as you've seen in the demo. So now we are going to jump into the next thing, and which is, it looks worse than it actually is, but this is simply put, how many random words do you want? In that case, these are 32-byte chunks. So what we have is we have 32 bytes chunks of random words, and which means if we have, for example, 18 random words, we multiply them by 32 bytes, then we're obviously going to get exactly 5 576 bytes of randomness, which should be more than enough for any use case that you would like to have. For example, if you have a, let's say you're going to have a KV store, a key value store, or let's say a different dApp, obviously you would pick a different input for this. So you would probably have a different data input. And then also you're going to define a callback gas limit, or in Solana, this is also seen as the compute limit, which means you are going to prepay and define basically how much gas or how much gas or compute units you want to have for the callback that the Solana relay is going to do when doing the callback from secret. Next, we're just going to use some small checks. That's not really important. Now, the next key thing is you are going to pack the data. So what we're having here is we have the data basically that will go into the contract on Secret Network, which means this is the data that you're actually going to pass in there. So in that case, we're just going to pass the data in, which says we just want to have 18 random words. So we're just going to pack the data. It's just a simple JSON encoded string. So there's not going to be like any extra work to be done. So pack the JSON with the data, just as a comment here. And then next and this is basically everything that you need to do. So at that point, what you did is we created the input, we created basically the request that the user can do. For example, in this case, it would just be how many random numbers do you want. You could also, of course, encrypt, for example, in a key value store example, you could potentially think about, well, maybe I want to encrypt a secret message, let's say some secret string or some link to whatever it could be. It's really up to you as a developer to decide. And you can just pack this inside of that data structure. Could be anything you want for the JSON. Next, we are going to have to do the usual things to access the contract. In that case, we're going to derive the gateway program-derived address and the task-derived program address. Idea behind it is the structure of Secret Path itself on Solana contains two accounts. One of these accounts contains the gateway state, which contains the task ID. So the gateway state contains a running number, which is the task ID, which means every task that you send into the Solana Secret Path contract actually gets its own task ID to identify. Which means you as a dev can always tag and see which task you actually have going around. So I'm actually going to put this as a hint for you here. The gateway task contains the task ID. Next, we are also going to need the address of the task PDA, which sounds worse than it actually is, but keep in mind, the gateway task only contains the task ID. And then we also can have an extra account, which takes care of essentially storing some essential information about the task that you're sending in. So what you're doing, right, you are sending in one task, which contains which simply contains the payload. And what the Secret Path contract will do is it will actually save this information. It will actually save what you've sent in, and it will later on verify and check if the stuff was actually correctly sent back to ensure that no manipulation was done along the way. Exactly. So what we're doing is essentially we are having the gateway PDA defined here. We're just using the standard functions from Web3 Solana to derive the program address. And next, we're going to do the same for the task state, which contains this vital information. So the task contains a payload hash. Task contains, so what we can have is contains the payload hash plus a small plus a check if the task was completed. So it just contains like a Boolean which checks was the task completed or not, because each task can only be let's write it down. Because the task contains the payload hash and a Boolean if the task was completed or not, because the task can only be executed once and not twice, just to make sure that we're not having possible replay attacks. Exactly. So now, since we got the tasks PDA as well, just using the normal find program address, we can go on and really go into the nitty-gritty of secret path now. Since we already got the encryption preparation done, now what we're going to do is we are always expecting a callback. So what we usually have for transaction flow is obviously you are going to send in a message into Solana. Then this message is then sent into secret using secret path, and then also, and that's important, that's also sent back using secret path. And secret path is then going to call the Solana contract again. And since Solana has its specialties, especially when it comes to doing callbacks, obviously you need to be able to know what accounts are going to be accessed and what programs are going to be accessed. And for this, the solution is rather simple. It's essentially doing the following. You on the front end are going to basically include a list of accounts that are going to be accessed using this. So that, to have a concrete example, means that we're going to include some test addresses. In that case, I just put some random addresses in, and these addresses are going to be included in these callback addresses. Bytes, essentially. So what we have is, if you have a callback address, which means this is callback addresses essentially is the following. It includes callback addresses, include all addresses that you want to have to be included in the callback. Means if you're doing a callback and you are trying to use that and see what needs to be included, you need to make sure that you include all callbacks to the addresses that you want. So let's say you have a callback and you want to access your whatever randomness contract you have, and you're going to access another task, or some other storage, or you're going to try to do some transfer LAMP ports or whatever you want to do. What's important is you need to include that callback address into your calls, because otherwise, if you don't, the callback will not be successful. So the callback addresses include all to be accessed accounts by you. What's important is this callback addresses will only include any extra accessed accounts. So what we have is essentially the secret path itself, and this is also a really important note, secret path itself will include obviously the task ID, the task state, will include the task state and the gateway state, as well as the programs, as well as the program ID itself. That will always be included by itself. Will include task state, gateway state, and program ID of the CPI of the callback, basically of the callback program. Will include this by itself. So it means for you as a developer, you will need to think about what accounts or callback addresses or accounts will essentially, you need to be thinking about this, what accounts aside from gateway state, task state, and normal program ID for CPI will need to be included into that list. You can pick whatever addresses you want. The relayer itself will then pick up these extra addresses that you defined there, and it will just include them into the callback. So yeah, this is really important. So of course, if you're missing this point, then the callback will not work and it will just fail. So keep in mind, when doing callbacks, you need to be able to know what accounts are going to be accessed at a later point in time. This is not really trivial, but since you're, for EVM users, this is really unusual, but for Solana, this is rather normal. So keep in mind, if you're coming from an EVM space, including these callback accounts or these accounts when accessing contracts is a rather normal thing. So yeah, next what we're going to do is we're going to look at basically what function you want to call in the callback. So first we just looked at what accounts are going to be accessed during the callback. Next, we're going to look at what function and what program ID is actually going to be accessed during the callback. And it's we kept it really to a really simple structure for this, since it's completely compatible with Anchor and is also completely compatible with just normal Solana program. We don't have to be super fancy with this. So to keep the whole shape of this in line with the EVM parts, we're going to do a very simple structure, which is the relay is going to look out for a callback selector, in which how it is in the EVM space, which is essentially just a program ID. So of the callback contract, or the callback account and callback program that you're having, you are only going to need the program ID, what you're going to access. So this is the program ID. And from your CPI, so you're doing a cross-program invocation, obviously, into that program. And you just need to define the program ID that you have here. So this is also, of course, going to be automatically included in the addresses here. And this program ID is going to be automatically included just to save you some, payload, some precious payload size that we need. But essentially, what you need to do as a developer is really just define, okay, what program am I going to call in a CPI, which is this program ID. And next, we are going to just concatenate. So this program ID is 32 bytes. And next, we're just going to concatenate 8 bytes for the function identifier. So since Anchor Solana uses a function identifier of 8 bytes, you can always just use these 8 bytes to identify your function. Of course, if you're not using Anchor, obviously, you can also use this as your custom function identifier. Important is that this size has to be 40 bytes, which means this is 32 bytes, and this here is really 8 bytes. You can pick these 8 bytes obviously how you want. I would definitely recommend using the Anchor framework, since this gives you an automatic function identifier, and this allows you to do the callback correctly. Again, the callback selector is just the program 32 bytes concatenated with the function identifier, which is 8 bytes. So in total, we have really 40 bytes in total for this callback selector. You can always use this as a check. So yeah. Next, we are going to do the following. So what we did is basically now we're just taking care of basically the way back, which contains all the addresses or the accounts that we want to access. And next, we defined what program we have and what function identifier we actually want to call. So yeah, this is one of the main things now. And now this is really going to get interesting, which is actually constructing a payload. In that case, we want to request the randomness. So this is actually the function name that we're going to call inside of our own secret path or own contract on secret. And next, we're going to construct a payload which contains the data, which I told you was here the number of random words. Next, we're going to define the routing info and code hash, which is actually which is simply put the contract address and contract code hash. And then we are going to define your encryption details, which means which address did you actually sign a message with, and which public key you have from your encryption. Plus, we're going to add the callback addresses or callback accounts. Plus, we're going to add the function selector and then the compute limits. As you can see, it's still kind of leaning towards EVM naming, but it really contains the whole structure was really made for EVM back then, and we kind of opted to stay a bit in line with the EVM naming. But since we kind of define what is what here, we can you can just use that seamlessly. As you can see, it just contains the same structures, and it just combines them in a clever way. So yeah, now really what we have to do is we constructed our payload, and next we are going to encode this payload. Really, that's going to be encrypted into a JSON. We are going to encrypt it using SHA-20 poly 3005. So after we created our shared key, as we said, using ECDH before, we are going to encrypt the payload using this, and we are off basically at that point with the encryption. So the encryption at that point is really done. It's like a super simple small function that really handles all the encryption for you. You just have to provide it with a random number unknowns in that case, and you will, and this for the demonstration purposes, we just opted to use a non-random number, but obviously we're going to do like a real random number later on. It's just for debugging. And what we're going to do now is so that's obviously for the demo, use just zeros for the nodes. Please use, of course, a random number. Please use a random number here. So obviously that's just for an example. So in that case, we can just get random values, or we can just initialize using random numbers. So basically, both are totally fine. Whatever you want to do. Exactly. So now we're going to encrypt the whole thing using charger 20 poly 1305, and we are going to concatenate this here, so the tag and the ciphertext plus the authentication tag that we have from poly 1305, and this creates our ciphertext. So this is actually the ciphertext that is going to be decrypted inside of the secret network gateway contract for secret path. This is actually the thing that's going to decrypt it. So since we now got our ciphertext correctly created, next what we're going to do is we're actually going to sign this payload hash. So what we do is we take the ciphertext, we just compute a catch-check to 56 hash of it. In that case, we kind of kept it in line with the EVM space, so we just use the normal catch-check to 56 from Ethereum, not specifically the SHA-3 algorithm, which is a slight variation. So yeah, we're just creating a payload hash, and what we're next doing is really, and this is really the important thing, this is what the user is going to see and what you also saw in the screenshot, which is we are just going to base 64 encode that payload actually, and then we're going to directly sign the base 64. Reason is Solana does not permit, obviously, does not permit you to sign any bytes, just to avoid any wallet drainers from hacking your wallet. Essentially, what it will do is it will instead take the base 64 of the payload hash, so as you can see here, and then we're going to directly sign the base 64 encoded string. So that way we can always ensure that we're always not signing any bytes. Instead, we're just encoding ASCII bytes, and encrypting the ASCII or signing the ASCII bytes is totally fine. And since the base 64 encoding is going to be deterministic, we can easily recover this and easily check the signatures against just the base 64 encoded string. So I think that's one of the key things for the encryption. Is there questions to this right now? That would be interesting. Other questions right now? I will just wait 1 or 2 minutes, and then we can do the last portion of it, because that's actually a bit easier part, I guess.
Did you see the question about gas on Secret versus Solana?
Okay, good point. How about Solana? No, interesting question. What is the price of using a smart contract only Secret versus Solana, even when it was like a contract containing a table of rows? Okay, so you want to store the data on Secret network. Is that the idea? For Greg, what's the price total gas prices? I mean, the problem is you can't really just use it to store arbitrary data, obviously, because there's also a gas limit in Secret network. So if you want to kind of circumvent paying high gas fees, you're probably not going to do it using this, because if you're storing that many data, obviously you're going to have a lot of gas costs incurred. That's also valid on Secret network. So Secret network obviously also pays for gas. I don't think it would be actually possible to do it like this. I think it should be like a bit. You probably should need like a smaller table of these rows. So probably like 100 times 100 should probably work, depending on what data you want to store. I'm assuming just like some bytes, I guess, not like a huge amount of bytes. The gas price itself really depends. The problem is you're going to have a lot of the data. For example, if you're doing it on Solana, obviously you're going to run into the payload limit, which the payload limit is around 1.5 kilobytes. So if you have more than 1.5 kilobytes in data you want to send over Solana, so you're going to have a hard time. What you could do is for EVM is obviously you could send over EVM because that doesn't really have a limit, but obviously you're going to have like pretty high gas cost just in EVM space itself. I would probably recommend we probably discuss it after this, but this is definitely a very good question. So thanks for asking. But it's definitely not like a super simple answer, I guess. We really have to do like some more calculation how's like, how many data you want to have, and then, what do you want to hide, and then, how you're going to go into Solana or not. Let's just continue with the code explanation, I think, because now what we're going to do is we just basically completed our payload, which is the encrypted part of the message. And next, what we're going to do is after signing it, we are just composing a execution info, which is just basically a huge blob that just contains all important info. Yeah, I mean, we can just discuss it afterwards. Thanks a lot, though, for the question. It was really nice. It's a really nice use case for the KV store example. So now, since we have the execution info, it's just basically composing everything into a complete package that is able to be used by the relay. So here we have the payload that really goes into the secret contract. And here we have the execution info, which contains this all-important info that we need, which is the user key, the public key, routing code hash, as we had before, the task destination network, which means we can pick basically to what network to send it to. In that case, we want to send it to secret networks testnet, which is Pulsar 3. So obviously Pulsar 3 is secret networks testnet. And we're going to send it into here. And then next, we're just composing the message. Essentially, you're putting in the nonce from the encryption. All this information needs to be passed onto the secret path Solana contract, and also need to be passed onto the secret path contract on secret, just to make sure basically to get the encryption done. Because the nonce, you need to know the nonce and the user public key to do the decryption and the encryption. Exactly. For this specifically, by the way, if there's certain questions for this coming up after this, or for someone who's watching this afterwards, not live, I would definitely recommend, please ask us if you have questions about this setup, and please have questions, if you have questions about the architecture or about using this, we're really happy to help you out. There's no dumb questions in this. This is really, what we did here is like super fresh out of our development pipeline, and we want to really get this into the hands of developers as soon as we can. So if you have questions, or if you think, something is confusing, please do not hesitate to ask us. So yeah, one of the last things that we're going to do still is just constructing, since we already constructed our execution information and our payloads, we're just going to have to bundle this into the contract, essentially just, bundle this together and send it off into Solana. That's it. So we're gonna have, send an information, our routing contract information, and our execution information, and that is it. This is all going to be sent into Solana. And at that point, we're just going to send in a transaction, sign a transaction using Phantom, for example, or your whatever Solana wallet you have, serialize the whole signature, and just send it into Solana. That's it. So at that point, we're just going to take it over basically into normal Solana, standard Solana methods. In that case, obviously we're using Anchor again for our framework, so we're just going to use the send function, and we're just sending in that message. That's it. So yeah, that is the whole code flow for the for Secret Path Solana. This here is just more debugging essentially, but that's it. So yeah, that is how the front end works. And now, just as a small example, but we will also recommend you essentially, this really handles the Solana side of handling these contracts. I would definitely recommend, before you go into Solana and dive into this, I would definitely also recommend diving into the EVM examples, because they also contain a bit more explanation about how the secret network side works about it. And since both of them are completely compatible, you can actually send messages, or you can actually do stuff from both chains. So you can potentially think about doing stuff from Solana and doing stuff from EVM, and basically put both of these information into the same contract as you have in Solana. So you could basically do like projects that span across two chains at the same time. Yeah. So questions about this? Something weird that you kind of saw, or something that kind of looks off? really happy to answer these questions. Sean, do you got any more questions or anything that you found interesting in this? Anything that you kind of found confusing maybe for some new devs?
I don't. Oh, someone's asking about function identifier. What is it exactly?
Very good question. So essentially, I can show you in the. So the problem about function identifiers is, so if you think about in the EVM space, you're only thinking about function selectors, right? These are like 4 bytes, which just define whatever function you're going to call. So for example, it's like 0x, AV, 0f, 00, whatever, 00, AA, or whatever. Just like this is like what you would have in the EVM space. And so we'd have a function selector in EVM space. And now the question really is, I'm also going to copy this into the code so everyone can see, just as an example. So what you usually have is, you would usually have this function selector in EVM, which calls your function. And now the question is there some sort of like equivalent in Solana that you can also use? And the question is, there actually is in the Anchor framework, and you just call it function, and that's why you just call it basically function identifier. But the idea behind it is the same as this function selector. It's just like it's like just 8 bytes that just define your function. That's it. Identifier. And in Solana, that it really is just, it's basically like the same thing as here. It's just 8 bytes basically, and not 4. The reason why, I don't know. But the core idea is basically that that's just in hex. And usually in Solana, you just define them using U8s. So you would just write that function basically as like a U8, a U8, just so which is like a byte. A U8, a U8, a U8, and a U8. So that's why it looks a bit funky. But I mean, it's the idea behind it is the same. It's just bytes that define basically what function inside of the contract you're going to, or the contract or the program you're going to call. I can show you what that means here in the case. I can also just share that screen, I guess. Can we? Does that work now? Oh. No, I can actually exit the screen. Let's pick that. Okay, let's pick that. I think that is showing now. Okay, no. Okay. And we can actually close this up as well. We can just jump to the other screen. Okay, which is this. So as you can see, basically, you have the whole thing written in Rust, obviously, because it's in Solana. And what a function identifier does, it will just basically point to this function here. It's just basically bytes that just point to this paired balance, for example, for the debug functions or for the randomness function, or it just points to the function that we're going to use, which is the send function, for example, or these function identifiers also point, which is actually in this part. So we have a small function that allows you to, yes, like, where do you have it here again? So in our case, we just created a small function that allows you to, you know, call. So in that case, for example, we have this, or we have, so basically what we have is we just basically have like a small function identifier that, you know, you have your function and you use these bytes to access this particular function. This is all what we really have. In that case, so there's like no extra steps needed. So essentially what you do is you build your contract, and then Solana will automatically create, or Anchor framework will directly create you for this, for example, for this name callback test, it will create a discriminator, which is this function identifier. These are like these 8 bytes, which points, when you call the contract, it will directly point you to this function as an entry point. You will basically enter the whole contract and will enter this function if you use this discriminator, these 8 bytes to identify it. Exactly. Yeah. Happy to answer that. Yeah. So there's a lot of it's like, so there's like certainly good differences between Solana and EVM. Fortunately, the anchor frame really tries to bridge a lot of these gaps with a lot of super nice concepts, which contains, for example, these function identifiers. Exactly. Yeah. So by the way, this is all of the code, which can of course all be seen in our repos. So we made a lot of optimizations to make sure that we really, squeeze out as much compute units as we can to make sure that the contract is, doesn't runs pretty lightweight. Yeah, we're really happy to just, if there's a dev who wants to use it, we're really happy to try it out. And also we're, really welcoming Solana developers onto Secret because, since the language is both in Rust, they will feel really comfortable using it. Yeah. So that's about for this workshop, and this is really just meant to give you a rather rough overview. And if there's more questions, really want to get the nitty-gritty of it, we're really happy to help you out after hours or like whenever you have time. Yeah, we're really keen on getting this, into a hackathon project. That would be really nice for us. We're really happy about it to, explore what devs can do with this. There's like a lot of possibilities there. Thank you. Let's just wait another 2-3 minutes, I guess, if there's more questions. And afterwards, we can probably end the workshop and the call today. And then see for next week. Basically, the end of the hackathon for HackSecret is pretty near. So we are very close, somewhat close to the end. So let's see what teams are coming in.
Thanks, Alex, for going so in depth. This was great.
Thank you. I mean, Solana is really special in this. It's extremely fast, and it's also really easy to work with once you have the knowledge. But the thing is, the learning curve for Solana is rather steep. But once you have it, it's actually really good to use, and it's really nice to use actually. But you really have to get used to it. So yeah. So if you have a Solana dev who's really willing to take this adventure, it will be rather easy for them actually. If someone's trying from EVM space, they will probably have a harder time. Exactly. Let's just wait another two minutes, and then we can close the call. Thanks everyone for being here today, and hope to see you in the next office hours next week, which will be at our normal dev call time, and we're just going to basically use it for dev call and for the hackathon simultaneously. Exactly. So next week, October 14th, is the next office hours, and then we can also do like a project review if someone wants to already show their project off. And then final submission time is next week, October 16th, which is all, you can all find that in DoraHacks. So the submission time is, the next dates are as follows. October 14th is office hours, and October 16th is the closing call. Submissions are due at 16 UTC. Thank you.